Question 4. Ethylamine and phenylamine, they are primary amines. Okay, so these are the structure, okay, of ethylamine and phenylamine. These two compounds, they are synthesized by different methods. Okay, part A. Several methods can be used to form ethylamine. Part 1. Ethylamine formed when ethane amide is reduced by lithium aluminum hydride. Write an equation for this reaction. Just use the H with square bracket to represent the atom of hydrogen, which used in the reducing agent. So for this ethane amide, first you need to know the oxygen must be removed. So 2 hydrogen needed to remove this oxygen, and after that another 2 hydrogen needed to bond with this carbon to form CH2. So that's why total it needs 4 hydrogen. So you just put 4 hydrogens here, then eventually you will form this ethylamine with the H2O. 2 hydrogens need to use to form the H2O. Another 2 hydrogen need to add to the carbon. Okay, part 2. Ethylamine is the product of the reactions of bromoethane with ammonia. This reaction you already learned that in the AS. Okay, so name the mechanism of this reaction and state the condition used. Okay, the name of mechanism is nucleophilic substitution. The nucleophile we use is the ammonia. Ammonia used to substitute the bromine. Okay, condition is ammonia with ethanol, heat under pressure. So this is the mechanism. Ammonia, the nitrogens with the lone pair attack this partial positive carbon. So after that, the CBr bond break. Okay, then these intermediate need to undergo deprotonation, means the NH bond break. These pair of electrons move to the nitrogen, okay, and it will form this ethylamine and H+. So this is a mechanism you learn or you know last time. So for part 3, you have to use a similar mechanism to deduce the answer. Okay, in the reactions A part 2, so it's formed secondary and tertiary amines. Suggest the identity of the secondary or tertiary amine formed in this reaction A part 2. So actually this one you have to think further. Means the ethylamines that form here, it's also will attack the reactant, means this haloalkane. So this bromoethane, because this ethylamine is also a base. So the nitrogens with the lone pair, this one also will attack the partial positive carbon, and the similar mechanisms will happen. Okay, CBr bond break, then it undergo deprotonation again, then it will form this secondary amine. So therefore, the identity of the secondary amine, it must be this one. So it's the CH3CH2, right, bracket 2 and H. So this is a secondary amines that form. Okay, so this one you have to understand how the things works. Okay, part B. Ethylamine is a weak base. State the relative basicity of ammonia, ethylamine, and phenylamine. So compare these 3 compounds. So these are the 3 compounds: the ammonia, ethylamine, and the phenylamine. From this comparison, we know that the ethylamine is the most basic compound. Why? Because the ethyl group is electron donating group. So the electrons will move to this nitrogen, and the electron density of the nitrogen will increase, and therefore the availability of the lone pair is more, and the ability for these nitrogens to donate its lone pair to H plus is greater. So that's why this is the most basic one, followed by ammonia. Then this one is the least basic. Why? Because the nitrogen has p orbital, and it can overlap with the pi electron system in the benzene ring, and therefore the lone pair on the nitrogen can delocalize into the ring, and this lone pair is less available. When it's less available means it's less able to donate to the H plus, so it's a weaker base. So this is how you explain for this basicity. Is the ability of the compound or this amine group donate its lone pair to the proton. Okay, so first you need to state the basicity. So the most basic is ethylamine, followed by ammonia, and last one is the phenylamine. Then you just explain like I told you just now. Okay, basicity is the ability of base to donate its lone pair to the proton. More available or more ability, so it will be a stronger base. So ethylamine is the most basic compound because it has one ethyl group, which is the electron donating group, and it will increase the electron density on nitrogen. So therefore this lone pair on nitrogen, it's more available and is able to donate to the proton. Phenylamine is the least basic because the p orbital from the nitrogen overlap with the pi electron system in the benzene ring, and therefore the lone pair will delocalize in the ring and the lone pair is less available. This is how you explain for this basicity. Part C. Pure phenylamine can be prepared from benzene ring in two steps. Draw the structure of the intermediate, suggest reagent and conditions for each step. In order to form the phenylamine from benzene ring, it must undergo nitration first. So benzene ring need to undergo nitration. The nitration mixture is the concentrated H2SO4 with concentrated HNO3. And the condition, it must be heat around 55 degrees C. Actually, it's 50 to 60 degrees C. We just take the average. So around 55 degrees C. Okay, after that, the benzene will undergo nitration, form nitrobenzene. Nitrobenzene is the intermediate. And we need to reduce this nitrobenzene, then it can form the phenylamine. In order to reduce the nitro groups here, so we must use tin with concentrated HCl, of course with heat. After that, must follow by sodium hydroxide, because we need to convert the compound to this amine. So therefore, at the end, you get this phenylamine. Okay, part D. For this reaction, it started with the phenylamine. Okay, so let's move on to the reaction 1. When the phenylamine reacts with the excess bromine, so first you need to know this phenylamine, this amine group is 2,4 directing. Means whenever there is a halogenation, this halogen will go to 2, 4, 6 position. Okay, this is the first, second, okay, third, fourth, fifth, and the last one. So whenever there is excess bromine, so this phenylamine, okay, if you undergo electrophilic substitution at 2, 4, 6 position, so it will form this 2, 4, 6 tribromophenylamine. So this is a compound that form W. So reaction 2, we need to know what is the products that form. So it's from benzene diazonium chloride. So from this phenylamine form benzene diazonium chloride, we must use the sodium nitrous with HCl. Why? Because the NaNO2, this sodium nitrous, with acid, it will form this HNO2, nitrous acid. So this HNO2 is the one that convert the phenylamine to this benzene diazonium ion or benzene diazonium chloride. There is a mechanism, but you no need to know the mechanism. So you just need to know the compounds that convert this phenylamine to this benzene diazonium chloride. Okay, so either you use this NaNO2 with HCl or you just put HNO2. It's actually better to put NaNO2 with HCl because HNO2 it need to form in situ. It need to form during reaction. Okay, after that, when the benzene diazonium chloride is formed, then if you react with the water, so it will form compound X. So this is reaction 3. So for this one, benzene diazonium chloride is actually not stable. When the temperature is more than 10 degrees C, if you get hydrolyzed, so it will react with water, and this one it will decompose and it will form this phenol. So the benzene diazonium chloride will decompose, okay, and form phenol. And the decomposition means it is involve water. Actually, it's some sort like a hydrolysis. So after that, when it's formed this phenol, the phenol is a compound X. And this benzene diazonium chloride will further react with the phenol and form this azo dye. This is azo dye. Okay, this is azo link. So the reaction is actually the electrophilic substitution. The benzene diazonium ion, this one, is the electrophile. If you react with the phenol, phenol is 2,4 directing. Again, this is 2,4 directing. So the benzene diazonium ion will substitute the hydrogens at this 4th position. So eventually it will be this part. So means it will form the azo dye later when it's react with the phenol. So this is actually the electrophilic substitution, or in general we call coupling reaction. And of course, this reaction means the reactions of phenol and benzene diazonium chloride, it must happen under alkaline condition. Sodium hydroxide needed. These are all the reactions that happen for this part D. Quite complicated. Okay, part 1. Draw the structure of W. I told you already just now. So it's a bromination of the phenylamine. So it will form 2, 4, 6 tribromophenylamine. Okay, just draw the structure like this. State the reagent used in reaction 2. Again, reaction 2 is this. From phenylamine to this benzene diazonium chloride. So what you need is sodium nitrous or NaNO2 with the HCl. Sodium nitrite with this HCl or the nitrous acid. Again, this is better. Sodium nitrite is better. Sodium nitrite with acid is better because when this sodium nitrite with the HCl, so it will form this nitrous acid. Okay, benzene diazonium chloride and the X reacts together in the reaction 4 to form Y. Again, the Y is the azo di here, right? So this is a reaction I told you already. The benzene diazonium chloride with phenol form this Y. So this is azo di. Okay, name the X, the organic product of reaction 3. So this is a phenol that formed from the benzene diazonium chloride. State the necessary condition for reaction 4, the last reaction. The reaction between the phenol and benzene diazonium chloride, it must happen under alkaline condition. So you just put sodium hydroxide, aqueous. Suggest the use of the Y. Y is an azo di, so you use as a dye. Part E. Methylamine is another primary amine, okay, which can act as the monodentate ligand. Define monodentate ligand, species that used one lone pair of electron to form single dative covalent bond with the central metal ion. So it's just one dative bonds form, right? Okay, copper 2 reacts with the phenylamine, the methylamine to form this complex ion. So this complex ion has the 2 methylamine and 4 H2O. So this one is the octahedral complex because it has 6 monodentate ligand. Again, 2 methylamine and 4 H2O, which is look like this or this. Okay, draw the 3-dimensional diagram to show the 2 geometrical isomers of this complex ion. Okay, so you must draw the trans and cis isomer. How to draw that? Okay, so the copper with the 2 bonding already given, you have to complete another 4 bonding. So in order to draw the 3D diagram, you must draw the ridge line and the dotted line. The ridge line is to show that this ligand is near to us. Dotted line is far away from us, is at the back. Okay, so another thing you have to be careful is you must put the donor atom to the bonding, means okay, the copper with this methylamine, this bonding must point to the donor atom. Donor atom is nitrogen because it has a lone pair to donate. And of course, for the copper with H2O, the bond must point to the oxygen. Okay, so you just do like this, OH2. And here is H2O. The bond must point to the donor atom. Okay, so this one, because the methylamine, now they are actually at different side, means the bond angle between them is 180. So this one is trans isomer. And when the methylamine, now they are at the same side, means the bond angle between them is 90 degree. This is a cis isomer. So you have to draw these 2 isomers. Okay, remember the charge, because all these monodentate ligand, the methylamine and the H2O, they are all neutral. That's why you need to use the charge of the copper ion, 2 positive. Okay, state the coordination numbers of copper in this complex ion. Very easy, because 6 dative bonds form 1, 2, 3, 4, 5, 6. So the coordination number is 6. Okay, part F. Cadmium ion form tetrahedral complexes with this methylamine, hydroxide and chloride. and equilibrium 1, 2, 3 is given, and the care step also given. So from here we know that the cadmium with the 4 hydroxide, this complex ion is the most stable complex. Why? Because the care step is the highest, means this one actually form more concentration or more amount. So that's why this is the most stable among this complex ion. Okay, part 1. Give the units of the care step for equilibrium 1. Equilibrium 1, then we need to know is the product over reactants, these two reactants, and therefore the unit is this mole per dm cube over mole power 5, okay, dm power negative 15, because the reactant, okay, is this and this, right? So therefore at the end you get this unit, okay, for equilibrium 1, mole power negative 4 dm chopped. Okay, write an expression for the care step for equilibrium 3. So again, care step is like the normal care C, right? So we use the concentration of the products over the concentration of the reactants. So the product is the complex ion, reactant is the cadmium ion, the concentration of cadmium ion, and the concentration of chloride power 4, because the coefficient is 4 here. Okay, now part 3. A solution of the chloride is added to this cadmium solution and allowed to reach equilibrium. The equilibrium concentrations given. So the cadmium ion, this concentration, chloride, this concentration. So substitute this concentration and the care step that given, and try to find the concentration of the complex ion. Okay, substitute this cadmium ion and this chloride concentration, so you get this 7.28 times 10 to the power negative 4 mole per dm cube. This is the concentration for the complex ion. Okay, part 4. When the methylamine is added to the cadmium solution, a mixture of this cadmium with the 4-methylamine and the cadmium with 4 hydroxides form. Okay, theoretically is supposed to form this, but still there are some amount of this cadmium with 4 hydroxides form. Why? Because we know that the phenylamine is actually a base, and this base, if you react with the water to form hydroxide and the ammonium salt. So when the hydroxide form, then this hydroxide will further react with the cadmium and form this complex ion. So that's the reason why, because the methylamine is a basic and is react with water to produce hydroxide. Okay, part 5. Cadmium ion exists as a complex ion. Okay, so this one is the cadmium with 6H2O. Identify the most stable and the least stable complex in table 4.1. Okay, so place one tick in each column. Okay, this one, the most stable, of course, from the care step I told you already, it must be the cadmium with 4 hydroxide. Okay, is the most stable one, because care step is higher. This one has the highest concentration. And the least stable, it must be the cadmium with 6H2O. Why? Because all the care step here, as you can see, all the care step here is more than 1. All this means the concentration of all these complex is going to be more than the complex ion with the 6H2O. Means all these complex is much more stable than the cadmium with 6H2O, right? Okay, that's why the least stable is the cadmium with the 6H2O. Okay, so least stable, and the most stable is the cadmium with 4 hydroxide. Okay, so you just explain like this because the cadmium with 4 hydroxide, okay, has the highest K step, and all the K step value more than 1 means all these complex, this, and this, okay, it's much more stable than this complex. Okay, that's all for this question. Thank you.